Close your eyes, dear traveler. Tonight we embark on humanity's greatest adventure, a journey to another world. We're going to Mars, the red planet, our nearest planetary neighbor, capable of supporting human exploration. We'll descend into the deepest canyons in the solar system, climb the tallest volcanoes ever discovered, and explore landscapes so alien, yet so hauntingly beautiful, they seem like dreams made real. Imagine yourself aboard a spacecraft, approaching Mars after a 6-month journey through the void. Through the window, the planet grows larger each day, transforming from a reddish star to a rust-colored disk to a world of stunning detail. You can see the polar ice caps gleaming white at the planet's poles, darker regions that early astronomers mistook for seas, and the enormous volcano Olympus Mons casting a shadow visible from space. Mars is smaller than Earth, about half the diameter, with only 38% of Earth's gravity. But it's still a world of epic scale, with features that dwarf anything on our home planet. The canyon system Valles Marineris stretches 4,000 kilometers, roughly the distance from New York to London. The volcano Olympus Mons rises 21 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. The atmosphere is thin, less than 1% the pressure of Earth's atmosphere at sea level, composed mostly of carbon dioxide, with traces of nitrogen and argon. You couldn't breathe it, and you'd need a pressure suit to survive. The temperature averages about 60 cc, though it can reach an almost comfortable 20 cc at equatorial noon in summer, or plunge to 125 cc at the winter poles. But Mars wasn't always this cold, dry, and barren. Billions of years ago, when the solar system was young, Mars was warmer and wetter. Liquid water flowed across its surface, cutting the canyons we're about to explore, possibly filling ancient seas, perhaps even supporting life. What happened to that ancient Mars? Where did the water go? Could life have evolved in those ancient seas? And if so, might it survive somewhere still? These are the questions that draw us to Mars, that make it the focus of intense scientific study, that make it the most likely destination for future human exploration. Mars is not just a dead rock in space. It's a world with a history, with mysteries waiting to be solved, with secrets written in its rocks and ice. Your spacecraft enters Mars orbit, swinging around the planet in a graceful arc. The deceleration pushes you gently into your seat as the orbital insertion burn slows your velocity, allowing Mars's gravity to capture you. Now you're in orbit, circling the planet every few hours, watching the surface scroll by beneath you. You've studied the maps, reviewed the mission plan, trained for months. Today, you'll descend to the surface in a landing craft, touching down on the edge of Valles Marineris. From there, you'll begin your exploration, on foot in your spacesuit, in a pressurized rover for longer distances, and even by small aircraft designed to fly in Mars's thin atmosphere. The landing site has been chosen carefully. Melas Chasma, one of the widest and deepest sections of Valles Marineris, with slopes and features accessible to exploration, and within range of the Tharsis volcanoes, Olympus Mons, Astrobiology Mons, Pavonis Mons, and Arsia Mons. The landing craft detaches from the orbiter with a gentle thud. Small thrusters fire, nudging you out of orbit, beginning your descent. Mars fills the window, no longer a distant world, but immediate, real, rushing up to meet you. The thin atmosphere begins to grip the craft, and you feel the first hints of deceleration. The heat shield glows red, then white, as friction turns your orbital velocity into heat. You're plunging through the Martian sky at thousands of kilometers per hour, a man-made meteor screaming toward the surface. The parachute deploys with a sharp jerk, slowing you further. Then the retro rockets fire, their roar transmitted through the craft's structure. The computer controls the descent, with precision far beyond human capability, adjusting thrust constantly to achieve a soft landing. The surface rushes up, reddish soil, scattered rocks, the vast canyon wall rising in the distance. 50 meters, 20 meters, 10 meters. Touchdown. The engines cut out, and silence falls. You've landed on Mars. The hatch opens, and you step out onto another world. The sky is butterscotch pink. Dust particles suspended in the thin atmosphere scatter light differently than on Earth. The sun is smaller, dimmer, about 2/3 the apparent size it appears from Earth. The horizon is closer. Mars' smaller size means the horizon is only about 3.5 kilometers away, compared to 5 kilometers on Earth. Before you stretches the Martian landscape, rolling plains of rusty red soil, scattered with rocks of all sizes, and in the distance, the edge of Valles Marineris, the grandest canyon in the solar system, waiting to reveal its secrets. Take a deep breath of your suit's recycled air. Feel the lightness of your body in the reduced gravity. You weigh less than half what you weigh on Earth. Feel the suit's warmth protecting you from the 50°C temperature outside. Your exploration is about to begin. You have weeks of traverses planned, sites to investigate, samples to collect, mysteries to unravel. You're going to walk where no human has walked before, see sights no human eyes have witnessed, and add your footprints to the ancient dust of an alien world. Are you ready? Then let's begin. Mars awaits, and it has secrets to share. Chapter 1. Valles Marineris, the Grand Canyon of Mars. You stand at the rim of Valles Marineris, and even though you've studied photographs and maps, even though you've trained on simulations, nothing has prepared you for the reality. The canyon yawns before you, so vast that your Earth-trained brain struggles to process the scale. The canyon stretches east and west as far as you can see, eventually disappearing over the horizon. It's up to 200 kilometers wide here in Melas Chasma. If you stood on one rim, you couldn't see the other rim even on the clearest day. And it's deep, 7 kilometers from rim to floor, deeper than the Grand Canyon, deeper than most of Earth's ocean trenches. The walls are layered in shades of red, brown, and tan, showing the geological history of Mars written in stone. Light and shadow play across the canyon's interior as the weak Martian sun moves across the sky, creating a landscape of sublime beauty and alien grandeur. Valles Marineris, Valley of the Mariner spacecraft, was named after Mariner 9, the spacecraft that discovered it in 1971, the first spacecraft to orbit Mars. It's not a single canyon, but a system of interconnected canyons, stretching about 4,000 kilometers across Mars's equatorial region, roughly 1/5 of the planet's circumference. If placed on Earth, it would stretch from New York to Los Angeles, or from London to the Sahara Desert and beyond. But Valles Marineris wasn't carved by water the way Earth's Grand Canyon was. It formed through a completely different process, tectonic rifting. Billions of years ago, as the massive Tharsis volcanic region to the west rose and swelled, the stress cracked Mars's crust, creating enormous faults. The ground dropped along these faults, forming the initial rift valleys. Over billions of years, erosion by wind, landslides, and possibly ancient floods widened and deepened the canyons, creating the spectacular feature you see before you. You're standing at the southern rim of Melas, the widest section of the valley system. Your mission is to descend into the canyon, explore its floor, examine the layered rock walls, search for evidence of past water, and hopefully for signs of ancient life. But first, you spend time simply observing from the rim. You set up instruments, a weather station that will monitor wind, temperature, and pressure, a seismometer to detect Marsquakes, cameras for panoramic photography. You take rock samples from the rim, carefully documenting each one, noting its position, orientation, and context. The rocks here are volcanic basalts, dark and fine-grained, formed from ancient lava flows. Mars was volcanically active for much of its history, and these rocks testify to eruptions billions of years ago when Mars was young and geologically alive. As you work, you notice the Martian wind. It's gentle. The thin atmosphere means even strong winds have little force, but persistent. Dust devils dance across the plain behind you, small whirlwinds that lift dust into spiral columns that can rise kilometers high. These dust devils are larger and last longer than Earth dust devils, sustained by the combination of solar heating and the dry, dusty surface. The sky is starting to darken. Sunset approaches. On Mars, with its thin atmosphere, there's little twilight. When the sun sets, darkness falls quickly. But before darkness, there's a spectacular show. The sun, smaller and dimmer than seen from Earth, touches the horizon. The sky near the sun turns from pink to deep blue, opposite of Earth's sunsets. This is because Martian dust scatters blue light forward and red light sideways, the reverse of Earth's atmospheric scattering. As the sun sets, you're looking through the dust toward the sun, so you see blue. The sun disappears, a small disk slipping below the horizon. For a moment, the sky remains light, glowing with scattered sunlight. Then darkness falls, and the stars emerge. Familiar constellations slightly shifted from their Earth positions, plus the two tiny moons of Mars. Phobos, the larger inner moon, rises in the west and sets in the east. Moving so fast, it crosses the sky in just 4 hours. It's an irregular chunk of rock, about 22 kilometers across, probably a captured asteroid. Through binoculars, you can see its cratered, potato-like shape. Deimos, the smaller outer moon, rises in the east like a proper moon should. But it's so small and distant, it looks like a bright star rather than a moon. It takes about 2.7 days to cross the sky from east to west. And there, brilliant in the evening sky, is Earth. The blue planet, your home, appears as a bright morning or evening star from Mars, sometimes accompanied by Earth's own moon as a tiny companion point. Looking at Earth from Mars's surface, you feel the distance, hundreds of millions of kilometers of empty space separating you from home. You retreat to your habitat module. a pressurized shelter where you can remove your suit, eat, rest, and prepare for tomorrow's expedition. Inside, you're warm and safe, but just centimeters away, beyond the habitat's walls, is the deadly Martian environment. Freezing cold, airless, radiation-bathed. You review tomorrow's plan. You'll descend into the canyon using a path your rovers have identified and prepared. A long slope where the canyon wall has partially collapsed, creating a navigable route. Once on the canyon floor, you'll explore, sample, and search for signs of water and life. As you drift off to sleep, you think about where you are. You're on Mars, standing at the edge of the grandest canyon in the solar system. Tomorrow, you'll descend into that canyon, walking where no human has walked before. It's terrifying and exhilarating in equal measure. Sleep comes, and with it, dreams of exploration, discovery, and the red world that has captured humanity's imagination for centuries. Chapter 2. Into the Abyss. Descending the Canyon. Morning on Mars. You wake to the habitat's alarm and the soft glow of lights simulating a sunrise. Outside, the real Martian dawn is breaking, the sky brightening from black to pink, the sun beginning its arc across the alien sky. After breakfast and suiting up, a process that takes about 30 minutes and requires careful attention to seals, life support, and communications, you exit the habitat. Your rover is waiting, a pressurized 6-wheeled vehicle that looks like a cross between a laboratory and a small apartment on wheels. The rover will carry you to the descent point and serve as your mobile base during the canyon exploration. It's equipped with scientific instruments, sample storage, a small pressurized cabin where you can remove your suit and rest, and enough supplies for several days of exploration. You climb in, seal the airlock, and start the electric motors. The rover moves almost silently. No engine roar, just the crunch of wheels on Martian soil. You drive toward the canyon rim, where the descent route begins. The route was chosen after careful analysis of orbital imagery and scouting by robotic rovers. It's a natural ramp formed by an ancient landslide where part of the canyon wall collapsed, creating a debris slope that extends from rim to floor. It's still steep, about 25-30 degrees, and it's strewn with boulders, but it's navigable with care. You pause at the rim and look down. The route descends into the canyon's depths, zigzagging between obstacles, disappearing into shadow partway down. It's a 7-kilometer vertical descent, higher than most mountains on Earth are tall, but in reverse, going down rather than up. You engage the rover's low gear and begin the descent. The wheels grip the loose soil, and the vehicle's sophisticated suspension adjusts constantly to keep the cabin level. You descend slowly, carefully, watching for obstacles, following the plotted route. The views are spectacular. As you descend, the opposite canyon wall becomes visible. Layered cliffs of sedimentary rock glowing in the morning light. The layers tell the story of Mars's geological history. Each band represents a different era, different conditions, possibly different climates. Some layers are volcanic, dark basalts from ancient lava flows. Others are sedimentary, lighter-colored rocks that may have been deposited by wind or water. Some layers show evidence of alteration by water. clays and sulfates that form only in the presence of liquid water. These altered layers are particularly interesting. They suggest that billions of years ago, when these rocks were exposed at the surface, water was present. Maybe flowing, maybe even forming lakes or seas. After several hours of careful driving, you're about halfway down. You stop to take samples and conduct measurements. Exiting the rover in your suit, you approach an exposed outcrop of layered rock. You use a hammer to chip off samples, placing each in a labeled bag. Back on Earth, or in your Mars-based laboratory, these samples will be analyzed in detail. Their composition, their age, the conditions under which they formed. You also deploy instruments. A portable spectrometer analyzes the rock composition without removing samples, using laser-induced breakdown spectroscopy to identify elements. Ground-penetrating radar maps the subsurface structure, looking for layers and voids beneath the surface. A magnetometer checks for magnetic signatures that might indicate the presence of magnetic minerals formed in water. The data is fascinating. The rocks show evidence of water, lots of it. The mineralogy suggests prolonged exposure to water, not just brief wetting, but extended periods when water was present. This area might have been lakeside or even underwater billions of years ago. You continue descending. The walls tower above you now, blocking much of the sky, creating a sense of enclosure despite the canyon's vast scale. The sun is visible only for part of the day. In the morning and evening, the walls shadow the canyon floor, creating periods of darkness and cold even deeper than usual Martian cold. As you near the bottom, you see something remarkable. Layers of white material interbed with the red rocks. You stop for a closer look. The white layers are composed of sulfate minerals, gypsum, epsomite, that form when salty water evaporates. These deposits are direct evidence of ancient water, possibly even ancient seas or lakes that filled this canyon billions of years ago. Finally, after a full day of careful descent, you reach the canyon floor. It's surprisingly flat and smooth in places, covered with fine dust and scattered rocks. In other places, dunes of red sand have formed, sculpted by winds channeled through the canyon. And in some areas, you see what might be dried mudflats. Polygonal cracks and fine-grained sediments, exactly like those formed when mud dries on Earth. You're 7 kilometers below the rim, deeper underground than any human has ever been on Earth. Though here you're not truly underground, just at the bottom of an incredibly deep valley. The air pressure here is slightly higher than on the rim. Mars's thin atmosphere pools in low places, but it's still far too low to breathe. The walls rise on both sides, stratified cliffs that would take days to climb. In places, massive landslides have dumped enormous piles of debris, house-sized boulders mixed with gravel and dust. These landslides might have been triggered by Marsquakes, by ice melting and destabilizing slopes, or by the sheer scale of the cliffs finally succumbing to billions of years of erosion. You set up camp on the canyon floor, parking the rover, deploying solar panels to recharge batteries, extending instruments. This will be your base for exploring the floor of Valles Marineris, the deepest accessible place on Mars. As evening falls and shadows fill the canyon, you sit in the rover's pressurized cabin, looking out at the alien landscape. Tomorrow, you'll explore further along the canyon floor, searching for more evidence of water, looking for organic compounds, hoping to find clues about whether life ever existed in this ancient valley. Tonight, you rest, 7 kilometers deep in the grandest canyon in the solar system, on a world that once had rivers and lakes and perhaps even life, and you wonder what secrets tomorrow will reveal. Chapter 3: Secrets in Stone. Reading Mars's History. Morning in the deep canyon brings a unique experience. The sun hasn't yet risen above the eastern wall, so the floor remains in shadow, lit only by reflected light from the opposite wall, creating a soft, diffused glow. The temperature is frigid, about 90 degrees, colder even than the Martian norm, because the canyon walls block the early morning sun. But you're warm in your suit and the rover's cabin. You've spent the night analyzing yesterday's samples and planning today's exploration. The goal is to search the canyon floor for more evidence of water and to look for organic compounds, carbon-based molecules that might indicate past life. After the suit-up routine and safety checks, you exit the rover and begin walking. The reduced gravity makes movement easy. You bound rather than walk, each step carrying you several meters. It's disorienting at first, but you adjust, learning to move efficiently in this alien environment. You're heading toward an area where orbital imagery showed unusual light-toned layered deposits, possibly sediments deposited in an ancient lake. If you can find and sample these deposits, they might contain organic molecules preserved from billions of years ago. The walk takes about an hour. The canyon floor is generally smooth, covered with fine red dust that puffs up with each footstep, hanging in the thin air longer than it would on Earth before settling. Occasionally, you detour around boulder fields or climb over small scarps where the floor has been offset by faults. The light gradually increases as the sun rises above the eastern wall. When direct sunlight finally strikes you, you feel the warmth even through your suit. The sun may be weak, but it's still the dominant heat source on Mars. You reach the target area. The light-toned deposits are exposed in a small cliff about 3 meters high. Layered sediments, each layer perhaps a centimeter thick, stacked in regular sequences. On Earth, such deposits form in lake beds, with each layer representing a season or year of sediment accumulation. You approach carefully, mindful that cliff edges can be unstable. Using a hammer, you extract samples from different layers, trying to get a vertical sequence that represents a time series, oldest at the bottom, youngest at the top. Back at the rover, you load samples into the portable analysis laboratory. The instruments here can't match the capabilities of laboratories on Earth, but they're remarkably sophisticated for field equipment. The X-ray fluorescence spectrometer identifies elements: silicon, aluminum, iron, calcium, sulfur, the basic constituents of Martian rocks, but in ratios that suggest sedimentary formation rather than volcanic origin. The mineral analyzer identifies clays, phyllosilicates, that form only in the presence of water. And crucially, it finds carbonates, minerals that form when CO2 dissolves in water. These minerals tell a story. Billions of years ago, this canyon didn't exist yet, or if it did, it was filled with water. A lake, maybe a sea. Sediments washed in from the surrounding highlands, settling in layers on the lake bottom. The water was mildly alkaline, allowing carbonates to precipitate. The climate was warmer and wetter than today, perhaps with rain or snow, certainly with liquid water stable at the surface. But the most exciting measurement comes from the organic molecule detector. This instrument uses gas chromatography mass spectrometry to search for carbon compounds. It identifies several simple hydrocarbons, aromatics, and what might be amino acids, the building blocks of proteins. Organic molecules on Mars. But what does it mean? Organic molecules aren't necessarily biological. They can form through non-biological chemical processes. Meteorites contain organic molecules formed in interstellar space or in the early solar system. Volcanic activity can produce organic compounds, and even modern Mars's surface chemistry might create some organic molecules. Still, the possibility is tantalizing. If these organic compounds are ancient, if they formed when the lake existed, they might be remnants of ancient life, or at least the chemistry that could have led to life. You need more samples, more data. You spend the day exploring the area, collecting systematically, documenting everything with photographs and notes. You find more layered deposits, more organic signatures, more evidence of an ancient watery environment. You also find something unexpected, a network of fine fractures in the rock, filled with lighter-colored minerals. On Earth, such fractures can form when microbial communities exploit cracks in rocks, creating microenvironments where they can access water and nutrients. Could these be microbial structures? Or are they purely geological features? There's no way to know for certain without more sophisticated analysis. The samples will eventually return to Earth. If not with you, then on a later sample return mission, where they can be examined with the full power of modern laboratories. Only then will scientists be able to say definitively whether these structures are biological or not. As the sun tracks across the narrow strip of sky visible from the canyon floor, you continue working. You deploy additional instruments, a magnetometer that detects ancient magnetic fields trapped in rocks, providing clues about Mars's lost magnetic field, a seismometer to listen for Marsquakes, cameras to document everything in high resolution. By late afternoon, you've amassed a substantial sample collection and dataset. The evidence for ancient water is overwhelming. The evidence for organic molecules is strong. The evidence for life remains ambiguous. Tantalizing hints, but no smoking gun. No undeniable biosignature. This is the nature of Mars exploration. The planet offers clues, whispers of what it once was, but it guards its secrets well. Each discovery raises new questions. Each answer leads to more mysteries. As evening approaches, you return to the rover, carefully stowing samples and data. Tomorrow, you'll begin the ascent back to the rim. A journey that will take at least as long as the descent. And then, you'll travel west, toward the Tharsis volcanoes, to explore another of Mars's extraordinary features. Tonight, you process data, catalog samples, and upload findings to the orbital relay that will transmit them to Earth. In a few months, when the orbital geometry is favorable, your findings will arrive at Earth, adding to humanity's growing understanding of Mars. You sleep in the deep canyon, surrounded by ancient rocks that once lay beneath a Martian sea, dreaming of the world Mars once was, and wondering if life ever gazed upon these same rocks billions of years ago. Chapter 4: The Ascent, Climbing to the Surface. The ascent from the canyon floor is, in many ways, more challenging than the descent. Going down, gravity helps. The rover's brakes and suspension do most of the work. Going up, you're fighting gravity every meter. And though Mars's gravity is weak, 7 kilometers is still 7 kilometers. You begin at dawn, when the sun first illuminates the canyon floor. The rover's electric motors whine as they engage, and you begin the long climb up the landslide slope. The route is the same as your descent, but it looks different from this direction. Obstacles appearing in different perspectives. Progress is slow, perhaps 1 or 2 kilometers per hour on the steepest sections. The motors strain, the battery charge drops steadily, and you stop frequently to rest the equipment and to take final samples from the canyon walls as you ascend. Each stop reveals new layers, new rock types, new chapters in Mars's history. You're climbing through time, with each 100 meters of elevation representing tens or hundreds of millions of years of geological history. At the bottom were the oldest rocks, possibly 4 billion years old or more. At the top will be younger deposits, perhaps only 3 billion years old. Still ancient by human timescales, but relatively recent in Mars's history. Some layers show clear evidence of water, clays, sulfates, carbonates. Others appear dry and volcanic. This alternation suggests that Mars's climate changed over time, with wet periods alternating with dry periods, perhaps driven by changes in the planet's axial tilt, volcanic activity affecting the atmosphere, or other factors we don't yet understand. About halfway up, you encounter something remarkable, a layer of conglomerate, a rock composed of rounded pebbles cemented together. On Earth, conglomerates form in riverbeds, with flowing water rounding and transporting the pebbles before depositing them. This Martian conglomerate is direct evidence that rivers once flowed into this canyon, carrying sediment from the highlands. You collect samples of the conglomerate, carefully extracting pebbles to analyze their composition. They're a mixture of basalts, sedimentary rocks, and altered minerals, exactly what you'd expect from a river draining a diverse landscape. As you climb higher, the temperature increases, not because you're getting closer to the sun. That effect is negligible, but because you're escaping the cold air that pools in the canyon bottom. By midday, when the sun is overhead, the temperature at your elevation might reach 30 cc, almost warm by Martian standards. The walls on either side remain towering presences, stratified cliffs that would take specialized climbing equipment and considerable courage to ascend directly. The landslide ramp is the only practical route, and even it requires careful navigation and constant attention to the rover's performance. After 2 full days of climbing, with an overnight stop on a relatively flat platform about halfway up, you finally approach the rim. The walls recede, the sky opens up, and you emerge onto the plateau that surrounds Valles Marineris. The contrast is striking. The canyon was enclosed, intimate despite its vast scale, with walls defining your world. The plateau is open, expansive, stretching to distant horizons in all directions except where the canyon cuts its great wound through Mars's surface. You've completed your exploration of Valles Marineris. You've descended into the deepest accessible depths, explored an ancient lake bed, found evidence of past water and intriguing organic molecules, and climbed back to the surface. It's been an extraordinary experience, but your mission is only half complete. Now you turn west, toward the distant volcanoes of Tharsis. They're not yet visible, too far beyond the horizon, but you know they're there, rising from the Martian surface like mountains touching space. Olympus Mons, the tallest mountain in the solar system. Astræus Mons, Pavonis Mons, Arcia Mons. The three Tharsis Montes that form a diagonal line across the Tharsis region. These volcanoes are your next destination, where Valles Marineris revealed Mars's watery past. The volcanoes will reveal its fiery past. The period when Mars was geologically active, when lava flowed across its surface, when volcanism shaped the planet's features and atmosphere. You begin driving west. The rover can travel about 30-40 kilometers per day over smooth terrain, less over rough ground. The Tharsis region is about 1,500 kilometers away, meaning the journey will take several weeks. But this is part of the adventure. You'll traverse a significant portion of Mars's equatorial region, seeing landscapes no human has seen before, conducting science along the way, experiencing the reality of long-distance travel on another planet. As the canyon recedes behind you and the western plains open before you, you feel the excitement of new discovery. Mars has revealed some of its secrets, but many more await. The volcanoes hold their own mysteries, their own stories of Mars's past, and perhaps clues to its future. The journey west begins. Chapter 5. The journey west, crossing the Martian plains. The traverse from Valles Marineris to Tharsis takes you across Syria Planum, a relatively smooth volcanic plain that slopes gently upward toward the Tharsis rise. It's a journey through geological monotony, kilometers upon kilometers of reddish soil, scattered rocks, and occasional impact craters. But it's never boring. Each day brings new vistas. The Martian landscape, despite its basic similarity, red soil, pink sky, distant horizons, has infinite subtle variations. The way light plays across the terrain at different times of day, the patterns of dust devil tracks crisscrossing the plains, the occasional boulder field or low ridge breaking the flatness. You travel during the day, when solar panels can charge the rover's batteries, and rest at night, when the temperature plunges and energy conservation becomes critical. Each evening, as the sun sets and Earth rises as an evening star, you process the day's findings, maintain equipment, eat a meal from the limited but nutritious supplies, and sleep. Along the way, you stop frequently to explore features of interest. An unusually large boulder, possibly ejected from a distant impact crater, reveals unusual mineralogy when analyzed, traces of olivine, a mineral that weathers quickly in the presence of water, suggesting this rock hasn't been exposed to water for eons. A small crater, perhaps 50 meters across and relatively fresh, maybe only a few million years old, provides a cross-section through the surface layers. You descend into it, sampling exposed bedrock, and find more evidence of volcanic activity. Basaltic lava flows stacked one atop another, representing multiple eruption events. You also encounter dust devils frequently. These whirlwinds are ubiquitous on Mars, particularly during the warmer seasons. They form when solar heating creates temperature differences in the near-surface atmosphere, causing air to rise in tight spirals. The rising air picks up dust, making the otherwise invisible vortex visible as a towering column of red dust. Most dust devils are harmless, even beneficial. They can clean dust off solar panels, improving their efficiency. But large ones can be dangerous, reducing visibility and potentially damaging equipment. You give them wide berth, pausing your traverse to watch them dance across the landscape, some reaching several kilometers high. About a week into the journey, you encounter a particularly interesting feature: a lava tube skylight. Lava tubes are cave-like structures formed when lava flows through channels, with the surface of the flow cooling and solidifying while molten lava continues flowing beneath. When the eruption ends, the lava drains away, leaving an empty tube. Sometimes, parts of the tube's roof collapse, creating skylights, holes that allow access to the tube. This skylight is about 20 meters across, with edges that drop vertically into darkness. Lava tubes are scientifically interesting and practically important. Scientifically, they preserve evidence of volcanic activity, protected from surface weathering. Practically, they could serve as natural shelters for future human bases. They're already sealed from the atmosphere, protected from radiation and temperature extremes, and potentially contain ice that could be extracted for water. You can't descend into this tube. It's too deep, and you lack the equipment. But you photograph it thoroughly, document its location, and deploy a small rover that can rappel down and explore the upper portions. The rover's cameras reveal a spacious tube extending in both directions, with a relatively flat floor covered with dust and fallen rocks. Continuing west, the landscape gradually changes. The terrain rises. You're climbing the gentle slope of the Tharsis Rise, a broad bulge in Mars's surface, created by the enormous mass of lava that erupted to form the Tharsis region. The slope is barely perceptible, perhaps 1 degree, but over hundreds of kilometers, you gain significant elevation. The atmospheric pressure decreases as you climb. Thin becomes thinner. At the same time, you begin to see evidence of Tharsis's volcanic nature. More lava flows, some young enough to have sharp, well-preserved flow features. Fields of volcanic cinder and ash, and eventually, in the distance, the first glimpse of the volcanoes themselves. It's late afternoon, with the sun low in the west, when you first see them. At first, they're barely visible. Dark smudges on the horizon, distinguished from landscape only by their regular conical shapes. But as you continue west over the following days, they grow, gradually dominating the western sky. Mons appears first, the northernmost of the 3 aligned Tharsis Montes. It's the tallest of the 3, rising about 18 kilometers above the surrounding plains. Even from hundreds of kilometers away, its perfect conical shape is evident. Then Mons comes into view, directly on Mars's equator, slightly smaller than Asreus, but still enormous by any standard. Finally, Mons, the southernmost and most massive of the 3, with a summit caldera over 100 kilometers across. And beyond them all, though still below the horizon from your current position, is Olympus Mons, the king of Martian volcanoes, the tallest mountain in the solar system. The sight of these volcanoes, even from this distance, is awe-inspiring. They're larger than anything on Earth, so large that they literally rise out of Mars's atmosphere at their summits, their peaks existing in near vacuum conditions, similar to low Mars orbit. You're still weeks away from reaching them, but already you can see your destination. Those volcanoes have been studied from orbit for decades, but no human has stood on their slopes, has climbed to their summits, has explored their calderas. That honor will be yours. The journey continues. Each day, the volcanoes grow larger, more detailed, more real. And with each day, your anticipation grows. What will you find on those volcanic slopes? What secrets do those ancient calderas hold? Mars is about to reveal another facet of its complex history. Chapter 6: Olympus Mons, the Mountain of Giants. After 3 weeks of travel across the Martian plains, you've finally arrived. You're parked at the base of Olympus Mons, looking up at the most extraordinary mountain in the solar system. It doesn't look like a mountain, not at first. The slope is too gentle, rising at only about 5 degrees on average. From your position at the base, you can't see the summit. It's beyond the horizon, hidden by the mountain's own curvature. Olympus Mons is so vast that it defeats human attempts to comprehend it visually. The numbers tell the story. Olympus Mons is approximately 600 kilometers across at its base, roughly the size of Arizona or the entire British Isles. It rises 21 kilometers above the surrounding plains and 25 kilometers above Mars's datum, the equivalent of sea level. If placed on Earth, its base would cover most of France, and its summit would extend well into the stratosphere, above most of Earth's atmosphere. But more impressive than the size is the structure. Olympus Mons is surrounded by a cliff called a scarp that rises 6 kilometers at its highest points. This cliff encircles the entire mountain, creating a barrier that early explorers will have to overcome to access the slopes. Fortunately, your landing site was chosen specifically for accessibility. You're at one of the few places where the scarp has been reduced by landslides and erosion, creating a ramp of sorts. Still steep, still challenging, but navigable with the rover. You begin the ascent. The scarp is the first obstacle. A cliff face of layered lava flows stacked one atop another. Each layer represents an eruption, a single flow or series of flows from a single eruptive episode. Counting the layers visible in the scarp gives a minimum count of eruptions. Hundreds, perhaps thousands. The ramp you're following is composed of debris, fragments of lava flows that have broken away from the scarp and tumbled down. The rover climbs slowly, wheels slipping occasionally on loose material, motors straining against Mars's gravity. Weak but not negligible when climbing 6 kilometers vertically. After a full day of climbing, you reach the top of the scarp and emerge onto the lower slopes of the volcano proper. The view is spectacular. Behind you, the Martian plains stretch to the eastern horizon, a rusty red expanse punctuated by distant craters. Ahead, The volcano slopes rise gently toward the still invisible summit. The surface here is lava, solidified flows with ropey, twisted textures called pauihe, a Hawaiian word, because Hawaiian volcanoes are Earth's closest analogs to Olympus Mons. Some flows are relatively smooth, others are jagged and broken. All are composed of basalt, the dark volcanic rock that's common on Mars, Earth's ocean floors, and the lunar maria. You stop to collect samples. The basalt here is ancient, but remarkably well preserved. No weathering, no erosion beyond what impact cratering and dust accumulation has caused. On Earth, these flows would have been eroded, oxidized, covered with vegetation, or subducted back into the planet's interior long ago. Here, they persist, frozen in time. Analysis reveals that the basalt is similar to Earth basalts, but with subtle differences. The composition suggests the magma came from deep in Mars's mantle, bringing up material that can tell us about the planet's interior. The age, determined by counting superimposed impact craters, is surprisingly young, perhaps only 100–200 million years. This is young in geological terms. These eruptions occurred long after the dinosaurs walked Earth, relatively recently on the Martian timeline. Olympus Mons might not be extinct. It could be dormant, capable of erupting again if Mars's interior heat can generate sufficient magma. You continue climbing. The days blur together, driving upslope, stopping to sample and measure, camping overnight, resuming in the morning. The slope remains gentle, but the altitude accumulates. 5 kilometers above the base, 10 kilometers, 15. At 15 kilometers elevation, something remarkable happens. You drive out of Mars's effective atmosphere. The atmospheric pressure, which was already barely measurable, drops to near zero. You're technically still on Mars's surface, but you're above almost all of the atmosphere, in conditions similar to orbital space. The sky changes. The butterscotch pink color fades, replaced by deep purple-black. Stars become visible even during daytime. The sun appears as an intensely bright disk against the black sky, surrounded by a faint corona. You're seeing the sun as astronauts see it from space. The temperature changes too. Without atmosphere to trap heat, the surface temperature swings wildly, hot in direct sunlight, approaching 20 cc, freezing in shadow, dropping below 100 cc. Your suit and rover must work harder to maintain stable temperatures. At 20 kilometers elevation, you're higher than any mountain on Earth, higher than Earth's highest flying aircraft typically fly, higher than most of Mars's atmosphere. Looking down, you can see the curve of Mars's horizon, the planet's surface falling away beneath you. Finally, after 2 weeks of climbing from the scarp base, you approach the summit. The slope levels out, and you see the caldera rim ahead, a circular cliff that drops into the volcano's summit depression. The caldera is enormous, about 80 kilometers across and up to 3 kilometers deep. It formed when the magma chamber beneath the volcano partially emptied during eruptions, and the summit collapsed into the void. Actually, there are multiple calderas nested within each other, representing multiple collapse events over the volcano's history. You drive carefully to the rim and look down. The caldera floor is relatively flat, covered with more lava flows, the most recent eruptions that partially filled the depression. Small cinder cones dot the floor, marking vents where the final eruptions occurred. Standing here, at the summit of Olympus Mons, you're at the highest point a human has ever reached on solid ground. You're 25 kilometers above Mars's datum, in near vacuum conditions, on top of a mountain so large it would barely fit within Earth's horizon, with views extending hundreds of kilometers in all directions. To the east, you can see back toward Valles Marineris, though the canyon itself is too far and too subtle to distinguish. To the south, the other Tharsis volcanoes, Astraeus, Pavonis, and Arcia, rise like smaller siblings, though each would be enormous on Earth. To the north and west, the Martian plains fade into hazy distance. You've climbed the tallest mountain in the solar system. You've walked on lava flows that might be the solar system's most recent volcanism on any terrestrial planet besides Earth. You've reached a place that humans have dreamed of visiting for decades. But your exploration isn't complete. The caldera below contains more secrets, and the other Tharsis volcanoes await. Your journey on Mars continues. Chapter 7: Into the Caldera, exploring the fire's source. Descending into Olympus Mons' caldera requires finding a path down the inner walls, steep cliffs that in places are nearly vertical. After scouting along the rim, you find a collapsed section where landslides have created a ramp similar to the scarp at the volcano's base. The descent is treacherous. The slope is steeper than anything you've navigated before, covered with loose debris that shifts under the rover's weight. You engage the lowest gear, rely heavily on the braking system, and descend in a series of switchbacks, constantly alert for instability. After several hours, you reach the caldera floor. It's like entering another world. The walls rise on all sides, creating a vast amphitheater kilometers across. The floor is relatively flat, covered with black basalt lava flows that show every texture: smooth poeho, jagged another Hawaiian term for rough lava, and pillowy formations suggesting lava erupted into or under ice. You drive toward the center of the caldera, where the most recent volcanic features are located. There's a cluster of cinder cones, small volcanoes built from fragments of lava ejected during explosive eruptions. They're small by Olympus Mons standards, perhaps 100-200 meters high, but they're fascinating because they represent the volcano's most recent activity. You park near one of the cinder cones and exit the rover to explore on foot. Walking across the caldera floor in your spacesuit, you're struck by the absolute silence. There's no atmosphere to carry sound, so except for the vibrations transmitted through your suit and the sounds of your own breathing and equipment, there's complete silence. The cinder cone slopes are steep, about 30-35 degrees, the natural angle of repose for loose volcanic debris. You climb carefully, your boots sinking slightly into the loose cinders with each step. The reduced gravity makes the climb easier than it would be on Earth, but the need for caution remains. A fall in a spacesuit could be dangerous. At the summit, you peer into the cone's crater, a bowl-shaped depression perhaps 20 meters across. The crater's interior is lined with splatter, frozen droplets of lava that were thrown into the air during the eruption, solidified in flight, and fell back around the vent. Some splatter droplets are fused together, others are separate. All are coated with the ever-present red dust. You collect samples, pieces of cinder, fragments of splatter, dust from the crater floor. Back at the rover, analysis reveals that these are indeed young, possibly only 100 million years old, perhaps even younger. The composition is basaltic, similar to the older flows, but with slight variations suggesting a slightly different source or different conditions in the magma chamber. There's also something unexpected: traces of water-altered minerals. Not much, just small amounts of clays and sulfates in fractures and vesicles, bubble holes in the volcanic rocks. This suggests that water, probably as ice, was present during or after these eruptions, perhaps melted by volcanic heat or trapped in the rock as it cooled. Water on Olympus Mons. This is significant. Scientists have long suspected that Mars's volcanic regions might contain subsurface ice, preserved in the cold Martian regolith, perhaps even melted occasionally by volcanic heat to create temporary hydrothermal systems. These minerals are evidence supporting that hypothesis. You spend several days exploring the caldera, documenting features, sampling different lava flows, climbing other cinder cones. Each feature tells part of the story of Olympus Mons's volcanic history, a history spanning hundreds of millions or perhaps billions of years, with countless eruptions gradually building the mountain to its current enormous size. You also deploy a seismometer, hoping to detect Marsquakes that might indicate current volcanic activity. Mars is much less seismically active than Earth. It lacks plate tectonics and has lower internal heat, but it's not completely dead. Occasional Marsquakes occur, and if Olympus Mons is indeed dormant rather than extinct, there might be detectable seismic signals from deep magma movement. The seismometer will remain here after you leave, transmitting data to orbital relays for years, listening for the planet's deep rumblings, perhaps detecting signs of life in Mars's interior. Not biological life, but geological life. The life of a world that's still warm inside, still capable of melting rock, and perhaps, someday, erupting again. As you prepare to leave the caldera and begin the descent from Olympus Mons, you reflect on what you've learned. This volcano, the largest in the solar system, is a monument to Mars's volcanic past. It grew slowly, eruption by eruption, over an immense span of time, much longer than Earth's volcanoes can survive before erosion or plate tectonics destroy them. Olympus Mons tells us that Mars was geologically active for much of its history, that volcanism shaped its surface and possibly its atmosphere, and that Mars might not be entirely dead even now. It also tells us that Mars, despite its small size, generated enormous amounts of magma, building volcanoes that dwarf anything on Earth. But why? Why is Olympus Mons so much larger than Earth's volcanoes? The answer lies in Mars's geology. Earth has plate tectonics. The crust moves, carrying volcanoes away from their magma sources, preventing any single volcano from growing too large. Hawaii, for example, is a chain of volcanoes created as the Pacific Plate moved over a stationary hotspot. Each volcano is extinct once it moves off the hotspot. Mars has no plate tectonics. Its crust is stationary. A volcano on Mars stays over its magma source for billions of years, growing with each eruption, never moving, never stopping until the heat source deep below finally exhausts itself. Olympus Mons is the result. Billions of years of eruptions building a single enormous mountain. You begin the long descent from Olympus Mons, leaving the caldera, navigating down the gentle slopes, finally descending the basal scarp to return to the surrounding plains. The journey down takes nearly as long as the ascent. This is a mountain measured in hundreds of kilometers, and traveling such distances, even downhill, requires time. But two more major Tharsis volcanoes await, Astrobiology Mons and Pavonis Mons. Each has its own character, its own features, its own secrets. Your exploration of Mars's volcanic wonders is far from complete. Chapter 8. The Three Sisters, Astrobiology, Pavonis, and Astrobiology Mons. The three aligned volcanoes of Tharsis, Astrobiology Mons, Pavonis Mons, and Astrobiology Mons, are often called the Tharsis Montes. They're arranged in a nearly straight line, running southwest from Olympus Mons. Each a giant in its own right, each unique in character. Your journey takes you first to Astrobiology Mons, the northernmost and tallest of the three, rising about 18 kilometers above the surrounding plains. It's slightly smaller than Olympus Mons, but still enormous, about 480 kilometers across at the base. Astrobiology Mons has a different character than Olympus Mons. Its slopes are steeper, its summit caldera smaller and deeper. Its lava flows younger and less eroded. The volcano appears more active, more recently erupted, perhaps more likely to erupt again. The climb to Astrobiology's summit takes about a week, following slopes that are noticeably steeper than Olympus Mons' gentle grades. The lava flows here show more variety. Some smooth poe-hoe, some rough some with channels where lava once flowed like rivers, now frozen as sinuous depressions across the volcanic surface. At the summit, the caldera is impressive, about 30 kilometers across and up to 3 kilometers deep. Smaller than Olympus Mons' caldera, but more dramatic because of its steeper walls. The floor shows evidence of recent volcanism, fresh-looking lava flows, cinder cones that appear almost pristine, impact craters that are sparse, because not enough time has passed for many impacts to occur. You explore the caldera, finding similar features to Olympus Mons, but with variations that suggest different eruption styles or different magma compositions. The seismometer you deploy here might provide comparative data with the one at Olympus Mons, helping scientists understand whether these volcanoes share a common deep magma source or have separate sources. From Astrobiology, you travel south to Pavonis Mons, located directly on Mars's equator. Pavonis is slightly smaller than Astrobiology, about 14 kilometers high and 375 kilometers across, but it has a unique feature that makes it particularly interesting: extensive lava tubes. Pavonis Mons is riddled with lava tubes, evident from orbital imagery as chains of collapse pits marking where tube roofs have fallen in. Some of these tubes are enormous, potentially large enough to drive a rover through, certainly large enough to house entire future bases. You spend time exploring the entrances to several tubes, rappelling into them where possible, sending robotic explorers into sections too dangerous or difficult for human access. The tubes are pristine, protected from surface weathering. They preserve volcanic features in perfect detail. You see where lava flowed along tube floors, leaving terraces marking different flow levels. You see skylights where sunlight penetrates, creating patches of light in otherwise total darkness. You see formations where lava stalactites dripped from tube ceilings, now frozen solid. These tubes are scientifically fascinating and practically important. Future Mars bases might be built in such tubes. They provide natural radiation shielding, protection from temperature extremes, and sealed volumes that could be pressurized with minimal structural additions. To reshape the planet's surface, one are probably comprehend, but they're also test and Mars's quieter present. These volcanoes are probably dormant now. Mars's interior has cooled over billions of years, and while it's not completely cold, the seismometers, the southern, is not extrabiero, or Mons extinct. Olympus Mons might erupt again someday, in 100,000 years, 1,000,000 years, or 10 million years. On geological timescales, might still be active, just sleeping for the moment. Your exploration of Mars's volcano, you've climbed Olympus features and added immeasurably to humanity's understanding of Martian volcanism. Now it's time to return home, or at least to return to your Mars base to prepare for the journey back to Earth. Chapter 9. The Return. Reflections on the Red Planet. The journey back to your base camp, near the original landing site at Valles Marineris, takes 3 weeks. You retrace your route across Syria Planum, driving east toward the rising sun each morning, camping under the stars each night. The return journey has a different character than the outbound voyage. Then, everything was new, unexplored, full of anticipation. Now, you know this route. You've seen these vistas, and your mind is full of what you've discovered, rather than what you might discover. You've been on Mars for 3 months. In that time, you've traveled over 3,000 kilometers, explored the deepest canyon and tallest mountains in the solar system, collected hundreds of samples, deployed multiple scientific instruments, and added countless observations to humanity's understanding of this alien world. The samples you've collected will keep scientists busy for years. The organic molecules from Valles Marineris will be analyzed exhaustively, tested for biosignatures, compared with terrestrial and meteoric organics. The volcanic rocks from the Tharsis volcanoes will be dated precisely, their compositions analyzed to understand Mars's interior. The water-altered minerals will reveal details of Mars's ancient climate. The seismometer network will operate for years, perhaps decades, listening to Mars's heartbeat, revealing its internal structure, detecting Marsquakes that tell us whether Mars is truly geologically dead or merely sleeping. Future missions might add more seismometers, creating a global network that can map Mars's interior with precision comparable to what we've achieved for Earth. As you drive east, you reflect on what Mars has revealed. It's a world of contrasts, ancient yet dynamic, cold yet once warm, barren yet possibly once alive. Its surface shows evidence of water, volcanism, impacts, wind erosion, and perhaps ice flow, creating a landscape of extraordinary complexity and beauty. Mars is also a world of mysteries. Where did its water go? The planet clearly had abundant water billions of years ago. Valles Marineris and countless other features prove it. But today, Mars is dry, with only polar ice caps and suspected subsurface ice. Some water escaped to space, lost when Mars's magnetic field shut down and solar winds stripped away the atmosphere. But much of it probably remains, frozen beneath the surface, waiting to be found and perhaps used by future explorers. Did life ever emerge on Mars? The evidence is tantalizing but inconclusive. The organic molecules could be biological, but they could also be abiotic. The layered sediments in Valles Marineris show that conditions suitable for life existed. Liquid water, chemical energy, protection from radiation. But finding definitive proof of ancient life will require more extensive exploration, deeper drilling, more sophisticated analysis. Is Mars still volcanically active? The young ages of some lava flows suggest that eruptions occurred relatively recently, and dormant doesn't mean extinct. Mars's interior is still warm. The seismometers will tell us how warm. If sufficient heat remains, magma might still form, and volcanoes might still erupt, though probably not on timescales relevant to human exploration. Can Mars be terraformed? This question, once purely speculative, becomes more concrete with each discovery. Mars has water, carbon dioxide, minerals needed for life. Its gravity, while low, might be sufficient for human health. Its day length, 24 hours 37 minutes, is close to Earth's. If we could warm the planet, thicken the atmosphere, and release the trapped water, Mars might become habitable. Not in decades, but perhaps in centuries or millennia. It's an ambitious vision, perhaps an impossible one. But Mars's secrets suggest it's not entirely fantasy. After 3 weeks of travel, you see the familiar landscape of your landing site. The habitat modules sit where you left them. Solar panels gleaming in the sunlight. The landing craft standing ready for your eventual departure. You've completed your surface exploration. Soon, you'll load your precious samples aboard the return vehicle, launch from Mars, and begin the 6-month journey back to Earth. Your time on Mars is ending. But Mars itself is not ending. It's a world that's endured for 4.5 billion years and will endure for billions more. Your footprints in the Martian dust will remain for centuries, undisturbed by wind or rain. A record of humanity's first steps on another world. The instruments you've deployed will continue their work long after you've left, and future explorers will follow, building on what you've learned, pushing further, discovering more. As you enter the habitat and begin the process of preparing for departure, packing samples, checking life support systems, reviewing the launch trajectory, you look out the window one more time at the Martian landscape. The pink sky, the red soil, the distant canyon rim, all illuminated by the small, distant sun. You've walked on Mars. You've descended into its deepest canyon, climbed its tallest mountain, touched its ancient rocks, breathed through your suit, its thin air. You've been part of humanity's age-old dream of exploring other worlds. And as you prepare to leave, you know that you're leaving part of yourself here, just as Mars has become part of you. The red planet's secrets, those you've discovered and those that remain hidden, will stay with you forever. Chapter 10: Legacy. Mars in Human History. As the countdown to launch proceeds, you have time to reflect on Mars's place in human history and imagination. Mars has captivated humans for as long as we've looked at the night sky. To ancient observers, Mars was the Red Wanderer, a star that moved against the fixed stars, changing position night by night. Its red color suggested blood, fire, war. Most cultures associated it with war gods. The Romans called it Mars, their god of war. The Greeks called it Ares, their war god. The ancient Egyptians called it Horus of the horizon, associating it with their falcon-headed war god. Mars's motion across the sky puzzled ancient astronomers. Sometimes it moved eastward relative to the stars, prograde motion. Sometimes it stopped, reverse direction, moved westward, retrograde motion, then reversed again. This complex dance wasn't understood until Copernicus, Kepler, and Newton revealed that Mars and Earth orbit the Sun, and retrograde motion is an optical effect when Earth, moving faster in its inner orbit, overtakes Mars. The telescope, invented in the early 1600s, revealed Mars as a world. Observers saw polar ice caps that grew and shrank with Martian seasons, dark markings that some interpreted as seas or vegetation, and occasionally bright clouds in the Martian sky. In 1877, Italian astronomer Giovanni Schiaparelli reported seeing canali on Mars, channels or grooves. In Italian, canali means channels, natural, or canals, artificial. But when translated to English, it became canals, suggesting artificial structures. American astronomer Percival Lowell took this idea and ran with it, mapping hundreds of canals and proposing that Mars was inhabited by an advanced civilization building planet-wide irrigation systems to transport water from polar caps to equatorial deserts. Lowell was wrong, but his Mars, a dying world where intelligent beings fought desperately against encroaching desertification, captured public imagination. H.G. Wells's War of the Worlds, 1898, depicted Martians invading Earth to escape their dying planet. Edgar Rice Burroughs' Barsoom novels, 1912 to 1943, depicted Mars as an ancient world with exotic civilizations. For decades, Mars in popular culture was a place of adventure, danger, and wonder. The space age brought reality to replace speculation. Mariner 4, flying by Mars in 1965, sent back the first close-up images: a cratered, moon-like surface, no canals, no cities, apparently lifeless. Early excitement gave way to disappointment. Mars appeared dead. But subsequent missions revealed more complexity. Mariner 9, 1971, orbited Mars and discovered Valles Marineris, Olympus Mons, and evidence of ancient river valleys. Mars wasn't dead. It was a world with a dramatic history, shaped by processes we were only beginning to understand. The Viking landers, 1976, searched for life with inconclusive results. They found an alien but fascinating world. Pink skies, red soil, cold but dynamic. The Viking images changed how humanity saw Mars, making it real, accessible, a place we might someday visit. Decades of robotic exploration followed. The Mars Global Surveyor, Mars Odyssey, Mars Express, Mars Reconnaissance Orbiter, each mapped Mars in increasing detail, finding evidence of past water, identifying mineral deposits, tracking seasonal changes. Landers and rovers, Pathfinder, Spirit, Opportunity, Phoenix, Curiosity, Perseverance, explored the surface, analyzed rocks, searched for organics, gradually building our understanding. And now, humans. Your mission is one of the first crewed expeditions to Mars, but it won't be the last. Plans are already underway for permanent bases, for larger exploration teams, for extended stays. Mars is becoming humanity's second home, not replacing Earth, but supplementing it, extending human civilization beyond a single planet. Why go to Mars? The reasons are manifold, scientific. Mars is a natural laboratory for understanding planetary evolution, climate change, geology, and potentially biology. It's similar enough to Earth to provide comparisons, different enough to reveal alternative pathways. Practical. Mars has resources that can support human presence: water ice, minerals, carbon dioxide for fuel production. It could become a stepping stone for exploring the outer solar system. Philosophical. Expanding to Mars reduces existential risk. Humanity on two worlds is less vulnerable to single-planet catastrophes. It also represents the human drive to explore, to expand, to seek new frontiers. Inspirational. Mars exploration inspires people, particularly young people, to study science and engineering. The Apollo moon landings inspired a generation. Mars exploration could inspire another. But Mars exploration also raises ethical questions. If Mars has life, even microbial life, do we have the right to contaminate it with Earth life? If we terraform Mars, are we destroying a pristine wilderness for our benefit? If we establish permanent settlements, who has sovereignty? Nations, corporations, humanity collectively? These questions don't have easy answers, but they must be asked. Mars is not just a resource to exploit or a destination to check off. It's a world in its own right, with its own history, its own character, potentially its own life. We must approach it with respect as well as ambition. The launch countdown reaches its final minutes. You're strapped into the return vehicle, samples secured, systems checked. Soon, you'll launch from Mars, beginning the journey home. As the final seconds count down, you look out at Mars one more time. The red soil, the pink sky, the distant canyon, the volcanoes beyond the horizon. This world has revealed some of its secrets to you, but many remain. Future explorers will uncover them, building on your work, pushing further, learning more. The engines ignite, the vehicle shakes, then lifts, accelerating upward, breaking free of Mars's gentle gravity. The surface recedes below you. Landing site, canyon, plains, volcanoes, all shrinking. The entire hemisphere of Mars rotating into view as you gain altitude. You're leaving Mars, but Mars isn't leaving you. Its rust-colored surface, its alien landscapes, its ancient mysteries, all will stay with you forever. You came to Mars seeking secrets, and you found them, written in canyon walls and volcanic slopes, in rocks and ice, in the very air and soil. Mars has been explored, but it's not yet understood. Mars has been visited, but not yet inhabited. Mars has revealed some secrets, but many remain hidden, waiting for future generations to discover. Your journey ends as you depart, but Mars's story continues. The red planet spins on, patient and eternal, keeping its remaining secrets while slowly revealing them, one discovery at a time, to those with the courage and curiosity to seek them. Epilogue: Dreams of Mars. Weeks later, in space between Mars and Earth, you float in zero gravity, looking back at the red planet through the spacecraft window. Mars is now a disk, smaller each day as the distance increases, but still visibly red, still visibly a world. From this distance, you can see whole hemispheres. You can see the Tharsis volcanoes as dark spots, Valles Marineris as a thin scar, the polar ice caps as white spots at the planet's poles. You can see Mars as a complete world, a planet, a place with its own identity. You think about what you've experienced. The descent into Valles Marineris, 7 kilometers deep, exploring ancient lake beds where water once flowed. The climb up Olympus Mons, 25 kilometers high, standing on the tallest mountain in the solar system. The samples you've collected, the data you've recorded, the discoveries you've made. You think about what Mars was. 4 billion years ago, Mars was warmer, wetter, possibly habitable. Rivers flowed, lakes filled valleys, rain or snow fell from thicker skies. Volcanoes erupted regularly, releasing gases that thickened the atmosphere, warmed the planet through greenhouse effects. Mars might have been Earth-like, a blue-green world of water and possibly life. What happened? Mars is smaller than Earth, with less internal heat. Its core cooled, its magnetic field shut down, and without magnetic protection, solar wind stripped away the atmosphere. Water froze or evaporated, escaping to space or retreating underground. The surface became cold, dry, hostile to life. Mars died, or at least fell into a deep sleep from which it might never wake. But Mars's past suggests possibilities for its future. The water is still there, frozen in polar caps, buried in permafrost. The carbon dioxide is there, frozen at the poles, absorbed in rocks. If we could warm Mars through deliberate terraforming or natural processes, those volatiles would release, thickening the atmosphere, warming the planet, potentially allowing liquid water to flow again. Could we terraform Mars? The technology doesn't exist yet, and the ethics are debatable, but it's theoretically possible. Deploy orbital mirrors to increase sunlight, release greenhouse gases to warm the atmosphere, seed the surface with engineered organisms to begin producing oxygen. Over centuries or millennia, Mars might transform, becoming a second Earth. Different in details, but similar in essentials. A world where humans could live without spacesuits, where ecosystems could develop. Or perhaps we'll live on Mars without terraforming it, in pressurized habitats, in underground cities, adapted to Mars as it is, rather than changing Mars to suit us. This approach is less ambitious, but more respectful of Mars's current state, and it's achievable with near-term technology. Either way, Mars's future likely includes humanity. You're part of the first wave, the explorers who paved the way, but others will follow. Settlers, scientists, entrepreneurs, adventurers, all drawn by Mars's challenges and opportunities. Your children or grandchildren might live on Mars. Future generations might be born there, growing up under pink skies, learning to walk in reduced gravity, calling Mars home. They'll explore further than you did, establish permanent bases, perhaps terraform the planet, making it truly habitable. And someday, looking back at Earth from Mars, they might see not one world with life, but two. Not one humanity, but one humanity on two worlds. The beginning of humanity's expansion into the solar system, and perhaps beyond. These are dreams, but dreams drive progress. Humans dreamed of flying for millennia before we achieved it. We dreamed of going to the moon for centuries before we landed there. We've dreamed of Mars for generations, and now we're there. Your dreams of Mars have been realized. You've walked on the red planet, explored its wonders, contributed to understanding it. But new dreams emerge. Permanent bases, self-sufficient colonies, perhaps terraforming, perhaps expansion beyond Mars to the asteroids, the moons of Jupiter and Saturn, and eventually other star systems. Mars is not the end of exploration. It's the beginning. It's the first world beyond Earth that humans will inhabit. The proof that we can live on other worlds, the stepping stone to the stars. As Mars continues to shrink in the window, as Earth grows brighter ahead, as your spacecraft carries you home, you carry Mars with you, in your samples, in your data, in your memories, in your dreams. You've touched another world. You've walked on Mars, and Mars in turn has touched you, changing you forever, making you part of its story, just as it's become part of yours. Good night, Red Planet. Good night, Valles Marineris. Good night, Olympus Mons. Good night to all the secrets revealed and those yet hidden. Thank you for welcoming us, for sharing your story, for allowing us to explore your ancient landscapes. Until we meet again, and we will meet again, for humanity's journey to Mars has only just begun. Farewell.